Today we are looking at question 1, differential equations. Consider two agents, j is equal to 1, 2, with their respective opinions, the vector sigma, which is sigma 1, sigma 2, based on the respective evidence, eta, vector eta, which is the vector eta 1, eta 2, and let the utility function of agent j be given by utility function j, which is a function of the vector sigma, is equal to eta j sigma j minus a half sigma j brackets r multiplied by the vector sigma close brackets j, where the matrix R is equal to R1 minus C subscript 1 2 minus C subscript 2 1 and then R2, with Rj being greater than 0 and Cj k greater than 0. Assume that each agent j chooses their own optimal opinion sigma j asterisk, which is giving the vector sigma asterisk, which equals to sigma 1 asterisk, sigma 2 asterisk. Calculate the first order conditions for finding the vector sigma asterisk and find the matrix M for which the vector eta is equal to the matrix M multiplied by the vector sigma asterisk. Cool. What we are first going to do is write down the equation for the first agent, which is j equal to 1. So when we do that, we get u1 brackets the vector sigma is equal to eta 1 sigma 1 minus a half sigma 1 brackets the matrix R multiplied by the vector sigma brackets 1. If we now begin by expanding and rewriting R multiplied by the vector sigma, we get brackets R1 minus C12 minus C21 R2 multiplied by sigma 1 sigma 2 close the brackets and then 1. We now multiply the matrices. We get R1 sigma 1 minus C12 sigma 2 and then minus C21 sigma 1 plus sigma 2 R2 and then brackets 1. So what this 1 outside the bracket means is that we just want this first entry or this first row for the equation of the first agent. So we can write this as eta 1 sigma 1 minus a half sigma 1 and then R1 sigma 1 minus C12 sigma 2. When we expand this out, we get eta 1 sigma 1 minus a half R1 sigma 1 squared plus a half C12 sigma 1 sigma 2. Now, we're going to work out the first order condition for agent 1. And to do this, we just need to differentiate partially with respect to sigma 1. And that's just because each agent j chooses their own optimal opinion. So this first agent's opinion isn't going to change due to the second agent's opinion, which is sigma 2. So when we do that, we get eta 1 minus R1 sigma 1 plus a half C12 sigma 2, which is going to be equal to 0. Doing the exact same thing for the second agent, so finding the equation for the second agent, we will get u2, the vector sigma, is equal to eta 2 sigma 2 minus a half sigma 2 r multiplied by the vector sigma brackets 2. So this time we want this second row for the second agent. So we get eta 2 sigma 2 minus a half sigma 2 brackets r2 sigma 2 minus c21 sigma 1. Expanding out the brackets, we get eta 2 sigma 2 minus a half r2 sigma 2 squared plus a half c21 sigma 1 sigma 2. If we work out the first order condition for agent 2, you will get eta 2 minus r2 sigma 2 plus a half c21 sigma 1, which is going to be equal to 0. So now if we write our first order conditions in a vector form, so we're going to do the partial derivative of the utility function for agent 1, which was partially differentiated with respect to sigma 1. And underneath that is going to be the utility function of the second agent, which was partially differentiated with respect to sigma 2. So this is just going to equal n1 minus r1 sigma 1 plus a half c12 sigma 2. So this first order condition, and then underneath that we're going to have this first order condition. So eta 2 minus r2 sigma 2 plus a half c21 sigma 1. Now this can be written as eta 1 eta 2 minus r1 minus a half c12 minus a half c21 r2 brackets sigma 1 sigma 2. And now this is simply the vector eta, and we have this matrix, and then this is simply the vector sigma, and this is going to be equal to 0 because the first order conditions are always equal to 0. So we can rewrite this as eta, the vector eta, is equal to r1 a half c12 a half c21 and then r2 and then the vector sigma. So just move that to that side. So that means that the vector m from over here is equal to r1 a half c12 a half c21 r2. Cool. So we've calculated the first order conditions and we have calculated the matrix M. Moving on, assume that R1 is equal to R2, which is equal to 1, and then C subscript 1, 2 is equal to C subscript 2, 1, which is equal to 2 over C, where with C is greater than 0, and that the two agents learn about their optimal choice by gradient learning in continuous time. So T is an element between 0 and infinity inclusively with a learning rate gamma. Calculate the system of differential equations describing this. Find the stationary state sigma s, which is a vector, so vector sigma s, as a function of the vector eta, which is eta 1 comma eta 2, and determine whether there is a range of values of c for which the stationary state is stable. Cool. So what we know from this line is that each agent is adjusting their opinion by gradient ascent on their own utility. So what that means is that we have these differential equations. So the function sigma 1, which is a function of t, which is being differentiated by t, is going to be equal to that learning rate, which is gamma, multiplied by the utility function of the first agent, which is being partially differentiated with respect to sigma 1. And that's just me writing this in mathematical terms. We have gradient ascent because this is positive and on their own utility, and this is what is showing that change in utility as the agent changes their opinion. So this we can write as gamma brackets, and then this was just our first order condition for that first agent, which was eta 1 minus sigma 1 plus 1 over c sigma 2. So that's just me submitting in I is equal to 1 and c21 is equal to 1 over c, 2 over c. Cool. If we do the same thing with the second agent, we get a very similar thing. So the same learning rate, but this time we have the utility function for agent 2, which is partially differentiated with respect to sigma 2. And so we get gamma eta 2 minus sigma 2 plus 1 over c sigma 1. Again, that's just me substituting in the values that were given above. Cool, so now we have this, and we need to work out the stationary state. To work out the stationary state, we need to know that the stationary state is when there's no change in the gradient / the opinion. So what that means is that these rates have to be equal to 0. When that is the case, we are left behind with two equations. 0 is equal to gamma eta 1 minus sigma 1 plus 1 over c sigma 2, and 0 is equal to gamma eta 2 minus sigma 2 plus 1 over c sigma 1. So now we must solve these two equations. What I'm first going to do is get rid of the gammas. So divide by gamma. And so we're left with eta 1 is equal to sigma 1 minus 1 over c sigma 2, and eta 2 is equal to sigma 2 minus 1 over c sigma 1. So we could solve this using simultaneous equations, or we can use matrices. If we were to use matrices, we would have the matrix 1 minus 1 over c 1 minus 1 over c1 bracket sigma 1 sigma 2 is equal to eta 1 eta 2, and we would then proceed by finding the inverse of this matrix, which I'm going to call A, and multiplying that by eta 1 and eta 2. I'm going to just choose to solve these simultaneously. In order to do that, I'm going to times this second equation by c. So I get eta 1 is equal to sigma 1 minus 1 over c sigma 2. Eta 2c is equal to c sigma 2 minus sigma 1. Plussing these two equations gets rid of sigma 1, and we are left with eta 1 plus eta 2c is equal to sigma 2 c minus 1 over c. And now we can write c minus 1 over c as c squared minus 1 all over c, and therefore sigma 2 is equal to c sigma 1 plus c squared, eta 2 and eta 1, all over, so that's me timesing by the c, and then all over c squared minus 1. So there's eta 1. To work out, there's sigma 2. To work out sigma 1, we will times the first equation by c and keep the second equation the same. When we do that, we get c eta 1 is equal to c sigma 1 minus sigma 2, and eta 2 is equal to sigma 2 minus 1 over c sigma 1. Again, if we plus these equations, sigma 2 cancels out, so we are left behind with c eta 1 plus eta 2 is equal to c minus 1 over c sigma 1. And so if we do the same thing as before, sigma 1 is equal to c squared eta 1 plus c and eta 2 over c squared minus 1. Cool. So the steady state is sigma 1 equal to c squared eta 1 plus c eta 2 all over c squared minus 1, and eta 2 is equal to c squared eta 2 plus c eta 1 all over c squared minus 1. Cool. So we have shown what the differential equations are, found the stationary state, and now we need to determine whether there is a range of values of c for which the stationary state is stable. So to look for the condition on c for stability, we need to know that stability requires both eigenvalues of the Jacobian matrix to be negative. So first what we have to do is work out the Jacobian. So to work out the Jacobian, we are going to look at our two differential equations and find the partial derivatives with respect to sigma 1 and sigma 2. So looking at our first differential equation and differentiating it partially with respect to sigma 1, we get minus 1. Differentiating it partially with respect to sigma 2, we get 1 over c. If we now look at this second equation, if we partially differentiate it with respect to sigma 1, we get 1 over c. And if we partially differentiate it with respect to sigma 2, we just get minus 1. So here is our Jacobian. What I have failed to do is just include that gamma. So our Jacobian will be this matrix multiplied by gamma. So here's our Jacobian. We now need to work out the eigenvalues of this Jacobian. In order to do that, we need to find a characteristic equation, which is done by solving the equation det of this Jacobian matrix minus lambda, the identity matrix, and we equate this to 0. So if we do this, we get minus gamma minus lambda, gamma over c, and gamma over c again, and then minus gamma minus lambda, and that's equal to 0. If we now work out the determinant, we have minus gamma minus lambda multiplied by minus gamma minus lambda minus these two multiplied, which will be gamma squared over c squared is equal to 0. Expanding the two brackets, we have gamma squared plus 2 gamma lambda plus lambda squared plus gamma squared over minus gamma squared over c squared is equal to 0. So we can write this as a quadratic. So lambda squared plus 2 gamma lambda plus lambda squared plus lambda squared over c squared is equal to 0. If we now use quadratic formula and work out the two solutions, or work out the two eigenvalues, we have minus 2 gamma plus or minus square root 4 gamma squared minus 4 brackets gamma squared plus gamma squared over c squared all over 2. So we can write this as minus 2 lambda plus or minus square root 4 gamma squared, and 4 gamma squared minus 4 gamma squared cancel out. So we're left behind with, that's my mistake, this should be a minus, and so should this. So we're left behind with 4 gamma squared over c squared all over 2. And so finally we have 2 gamma plus or minus 2 gamma over c all over 2, which can be written as minus gamma plus or minus gamma over c. And if we just factorize out the gamma, we have minus gamma 1 plus or minus 1 over c. So our two eigenvalues are minus gamma 1 plus 1 over c, and our second eigenvalue is minus gamma 1 minus 1 over c. Cool, so like I mentioned before, stability requires both of the eigenvalues to be negative. So we can see that this bracket is always going to be positive, and so positive times this negative will be a negative. So the first eigenvalue is always negative. Now here we need to make sure that this bracket 1 minus 1 over c is always positive. So 1 minus 1 over c always positive. That way we can make sure that this second eigenvalue is always going to be negative. So if we now solve this inequality, we have 1 greater than 1 over c, and so c is greater than 1. So the condition required for stability is c greater than 1. Cool. If we just fill that in, so over here we have gamma e to 1 minus sigma 1 plus 1 over c sigma 2, and gamma e to 2 minus sigma 2 plus 1 over c sigma 1. Our stationary state was c squared a to 1 plus c a to 2 all over c squared minus 1, and then it was c squared a to 2 plus c a to 1 all over c squared minus 1. And the condition on c for stability is c has to be greater than 1. Cool. Hopefully that made sense. Part C, demonstrate that the general solution is the vector sigma, which is a function of t, is equal to e to the power of gamma mt multiplied by the vector sigma 0 minus the vector sigma s, close bracket, plus the vector sigma s for the constant matrix M, and calculate e to the power of y mt. Okay, cool. We are first going to start off with our differential equations, which I'm going to write as the vector sigma, which is a function of t, which was equal to gamma eta, the vector eta, minus gamma a multiplied by the vector sigma t. So this is just me writing our two differential equations as one thing. But of course I've not included d over dt, so I need to include that, and to include that I'm just going to add a dot in on top of this sigma, and all that means is that you are differentiating with respect to time, or t. Cool, so now we have this. Now I'm going to define a new function, so xt, which is going to be equal to sigma t minus the steady state. And all that is saying is that there's just a small deviation away from the steady state. That's all that this equation is saying. So what I now need to try and do is substitute this new function into this previous function. In order to do that, I need to first differentiate this function with respect to t in order to substitute it into here. When I do that, I get x dot t. So I've differentiated that with respect to time, and that's going to be equal to sigma dot. So I'm differentiating this with respect to time as well, and this is just the constant, so it disappears. So now we get x dot t is equal to yn minus ya, and sigma t can be written differently using this equation. It can be written as xt, x which is a function of t, plus sigma s. Cool. Now if I expand the bracket, we get gamma a x, which is a function of t, minus gamma a sigma s. I've just noticed that I've forgotten to define what a is. A is just our matrix 1 minus 1 over c minus 1 over c 1, which is the matrix that you get when you take the coefficients of sigma 1 and sigma 2 in these two equations. In fact, I'm going to go back and change this matrix just to be m, as that is what they've used in the question. Cool. Okay, so now we have this new equation, and what we should notice is that gamma eta is going to be equal to gamma m sigma, the steady state. And why is that? That is because if we go back to over here, when we were solving for the steady state, we were essentially doing this matrix A, which is now called M, multiplied by sigma and equaling that to eta. So this is eta is equal to M multiplied by the vector sigma, and this vector sigma gave us the steady state. So we can write this vector as S. And if you notice before, we divided by gamma. So if we bring back that gamma, we get gamma eta, the vector eta, is equal to gamma m, the vector sigma s. So we get this is equal to that, and that's exactly what we have over here. So all that means is that these two will cancel out, because when I move this to the side, we're going to be left behind with 0. Cool, so that means xt which is differentiated with respect to t, is equal to minus gamma mx t. If I now write this in a different way, we can write it as dxt over dt. So that dot representing the dt is equal to minus gamma mx t. So this is a differential equation. If we now solve this differential equation by moving this to this side and moving the dt to this side, we get xt dx t is equal to minus gamma m dt. Integrating both sides, sorry, this should be 1 over x t. Integrating both sides, we get ln x t is equal to minus gamma m t plus c. Raising both sides to the power of e gives us x t is equal to e minus y, or gamma, mt plus c, which can be written as xt is equal to e minus gamma mt multiplied by e to the power of c. We now substitute t is equal to 0, because that is our starting point. We are left behind with ec, or e to the power of c, is equal to x0. So finally we can write xt, so x, which is a function of t, is equal to e to the power of minus gamma mt multiplied by x0. Now, if we substitute this equation into this equation over here, we get, if I write it over here, we get e to the power of minus gamma mt x0 is equal to sigma t minus sigma s, the vector sigma s. Cool. Now what we must do is change this x0 in terms of sigma. So we're going to substitute this into this same equation, and what that gives us is e to the power of minus gamma mt brackets sigma 0 minus sigma s is equal to sigma t minus sigma s. And so moving this to the other side, we get sigma t is equal to e to the power of gamma mt sigma 0 minus sigma s plus sigma s, which is what they wanted. Cool. Hopefully that all made sense, and that will be the end of question 1.